So this one. All right. Hello, everyone. Thanks for coming. So my name is Antonin Bass. I'm a software engineer at Barefoot Networks, a company that makes P4 programmable silicon. And I've been involved with P4.org for a while now, pretty much since P4, the P4 effort was started. So these are the objectives of this tutorial session. So of course, we'd like you to find out about the P4 programming language, which is a domain-specific language for networking applications. So why did we introduce this language and what it is used for today? We'd also like you to find out about the P4 software tools developed by the P4.org community, which includes the P4 compiler, BMV2, which is a software switch to enable development of P4 data planes and P4 applications, and P4 runtime, which is a runtime interface for P4 forwarding planes. And it's a bit similar to OpenFlow in a way. So let's start with Delaplane programming. What is Delaplane programming? Why do we need it? And how does it relate to P4? So because P4 is often associated with SDN, early on in the existence of P4, there was a lot of press saying P4 is going to be OpenFlow version 2. And because SDN is often associated with OpenFlow itself, I think it's important to start with a little recap on what SDN is and what OpenFlow is. So SDN is essentially the separation of a centralized control plane and a distributed data plane. So instead of having them be on the same box, the idea is to decouple them and have one centralized controller control multiple switch boxes, which kind of like become dumb because you're taking the brain out of the switch box and putting it in your centralized control plane. OpenFlow is often seen as a fundamental part of SDN. It's a technology that has enabled SDN principles, that separation of the control plane and data plane, to be deployed in many networks. Thanks to two things. A standardized model for packet processing. More precisely, it's a logical view of how packets are processed, which is exposed to the remote controller. In other words, it's essentially the algorithms which is used by the networking device to process packets. And so at the center of this standardized model is the match action abstraction. And in the original version of OpenFlow, OpenFlow 1.0, you have one big match action table which matches on every packet and takes action if a rule was inserted for that specific packet by the controller. And that table was a big table which was basically matching on 12 protocol fields. So your Ethernet fields, your IPv4 fields, some VLAN fields. And the other thing contributed by OpenFlow is a standardized communication protocol between the control plane and the OpenFlow agent running on the switch. And through that protocol, the controller is able to insert and modify rules into that big flow table I was talking about and query statistics from the device. So why do we have this concept of logically centralized control versus running a distributed control plane on every switch device? Why does it get us? Well, if you have a single control plane, it has a view of the entire network, and so it's able to run routing algorithms and distribute those routes to every device in the network much faster and much more easily than if you have to run a distributed routing algorithm in every node and wait for those independent algorithms which receive information from their neighbors to converge. It's also much easier to enforce granular policies such as security policies at the network level. You can decide in one central place which kind of security policies you want to enforce in your network and then program the ACLs in every device accordingly. So one issue with OpenFlow is that to support new networking protocols, usually you have to move to a new OpenFlow versions. And so even though we started with 12 protocols in OpenFlow 1.0, protocols have been added. OpenFlow has been modified to support up to, I think, 40 protocols today. So basically, in a way, the interface changes and evolves as you need to support more protocols. OpenFlow 1.0 also had another issue, which was it was, in a way, hard to implement efficiently on existing networking hardware because OpenFlow 1.0 has that abstraction of one big match action table, but that's not usually how switch silicon works. Usually switch silicon has many tables. You have your L2 tables, your routing tables, your ACL tables that you can organize in a certain way. And so it was actually quite difficult, I believe, to map that abstraction of one match action table to hardware efficiently, which is why in subsequent versions of OpenFlow, there was something called TTP table type pattern, which was introduced. And kind of like instead of having that one standardized switching model, how the switch is supposed to process packets, what happened is that vendors could now, using a table type pattern, describe what their hardware was actually doing, the tables that their hardware was actually supporting. So that gave the controllers the ability to program that hardware more efficiently, but there was one cost, which is that now the controller had to handle differences between different vendors itself instead of relying on one unified protocol and standardized model. And so that led to a lot of complexity for controllers which wanted to be multi-vendors because now the southbound interface, how they communicate with the OpenFlow agent on the switch, had to be slightly different based on which switch silicon the controller was talking to. And that brings us to P4. What is P4? Well, P4 wants to take things like one step further by enabling the control plane essentially to decide, and the network operators to decide exactly what the networking device is supposed to do. So that relies on the existence of a new class of networking hardware, which we can call P4 Programmable, which can take that P4 programming language and implement it. And in particular with P4, and like with OpenFlow, we don't assume specific protocols. We don't assume specific packet headers. It's up to you to decide which headers your program and your networking device are going to support. And that takes us to, and that takes us to our idea of how networks should be designed today. So first, what is going on now without P4? Let's say you're a network designer, you need to design a network, you need to provision it, buy the equipment, and you have a certain set of requirements. So power requirements, throughput requirements, how much throughput should my network be able to handle, and obviously feature requirements, which protocols you want to be able to use in your network. And so what you do when you're a network designer and you need to provision a network like this is you go to OEMs, you look at different pieces of equipment, you look at the data sheet, which is essentially like a description in English of what the networking device is capable of. And you basically look for the device that matches what you want to do. So a device that can support all the protocols you want to support and so on. And once you decide on a chip, it's going to determine how you build your network, because you're going to build your network to work with that specific hardware instance. The issue for us is that what we think is, maybe you can find a piece of equipment which is going to satisfy all of your requirements, but it's very likely that that networking device is going to have more features than you actually need. So in one way, I think it's fair to say that you're paying for features you don't actually need. And we believe that that equipment may not be future-proof. Maybe in the future, you want to support new protocols, in which case you would have to wait for a next generation of networking devices. And actually, it's very rare in the industry to be able to come up with your own protocols and convince a silicon vendor to implement your protocol, your idea, in the next generation of silicon. Not only is it difficult, you need to have a lot of traction, but it can take a long time. You have to wait for the one hardware development cycle, so it can take like a few years. So with P4, we're trying to change this philosophy from bottom-up design to top-down design. With top-down design, you decide how you want your network to process packets. And you're the one telling the network how to process packets. And how do you do that? Well, you get some hardware, which is P4 programmable, and then you write your own P4 program, which describes exactly how the hardware should process every packet. Once you write your P4 program, you give it to a P4 compiler, which is going to translate it to some representation that the hardware can understand. And so now you have control over which features you support in your network, and you don't have to rely on third-party chip vendors to essentially make the decisions for you and tell you which features you can use in your networks. So here are a few benefits of Delaplane programmability. Just what I just said was the ability to add new protocols in the future. You can buy some equipment today and know that you're going to be able to support any protocol of your choice in the future simply by writing a new P4 program. A very important aspect is the ability to reduce complexity. You can actually remove unused protocols and unused features from your program when you stop requiring them, and you only include in your program the features you actually need, which means that you can get a better use of hardware resources in your programmable hardware. A lot of fixed function devices, and by fixed function I mean devices that cannot be programmed. So the behavior is determined when the silicon is made by the silicon vendor. Well, there are some resources which are allocated for different features, and if you don't require those features, you still have to pay the cost in a way. You cannot use those hardware resources, those memories, those SRAMs, or those TCAMs for something else. You always have some flexibility in how you can allocate your TCAMs often to program your ACLs differently. Usually you have some flexibility in your routing table. You can choose how to partition your table between V4 addresses and V6 addresses, but you're very limited in how you can reallocate, repurpose resources. With a programmable device, if all you're interested in is being able to do L3 routing and scale up your routing tables for V4 or V6 as much as possible, you can do it and reach like millions of entries. Greater visibility, and I'm going to talk about this a little bit further afterwards, but thanks to Delaplane Programming, we're able to get greater visibility into the network. We can gather statistics much more efficiently than before and for whichever purpose we desire. Additionally, we bring software style development to the network. So because now your devices are programmable, we enable rapid design cycle, fast innovation. The ability to fix Delaplane's bugs in the field, it's just like rolling one more software update. So just like you can update your operating system running on the switch, you can also roll out updates to actually update the packet processing engine on the switch. And finally, you keep your own ideas. If you come up with a protocol, then that IP belongs to you. You can integrate it in your own P4 programs. You don't have to share them outside. And in particular, you don't have to share them with a silicon vendor, which can then integrate your design in their chip so that it works for you, but that chip is also sold to many, many people. So basically, if you come up with a new protocol and if you want to integrate it in some switching ASIC, it becomes available to everyone. But with P4, you can actually keep that IP to yourself. Here is a list of a few programmable network devices that support P4 today. they are organized in different categories based on like the speeds and feeds of the devices here. So you have some flexible P4 programmable ASICs, such as the Barefoot Tofino ASIC and the Barefoot Tofino 2 ASIC, which are 6.4 terabits and 12.8 terabits data center class ASICs. You have the Spectrum family from Mellanox. You have an ASIC from Cisco. You have an ASIC from Intel as well. Then you have NPUs. NPUs have always been like programmable, right? They don't run at the same speeds as switching ASICs, like the ones I just mentioned, but they've always been programmable in a way. Usually programmable through C or potentially vendor-specific languages. So there was nothing stopping NPUs from also being P4 programmable. If you can be programmed using C, it stands that you can be programmed using P4, which is supposedly easier to compile to networking hardware. Then we have a few CPU targets, virtual switches. There was a project called Pisces for Open vSwitch, where the goal was to introduce a programmable parser, just like in P4, into OVS, so that it's much easier to roll out OVS releases, which can support new protocols. And finally, you have like P4 compilers available for some FPGAs. For example, Xilinx has a P4 compiler which is integrated into the workflow for programming the NetFPGA platform, which is a FPGA platform which is very popular with academics mainly. So for those devices, you're in charge of telling them how to process packets by writing a P4 program. A few popular P4 applications which exist today. So most of those papers have been published in high-profile conferences such as SIGCOMM. We have a layer 4 load balancer. Usually, layer 4 load balancing is done in some dedicated hardware, dedicated appliances. So now with P4, I think this paper showed that you can actually implement a layer 4 load balancer in P4 in a commodity switch, commodity P4 programmable switch. Some new transport protocols like NDP, which aims at reducing the latency in data center communications. So NDP is interesting because it relies on some new networking primitives which cannot be implemented with today's hardware, today's fixed function hardware, which is not P4 programmable. For example, NDP maintains very small queues at the switch, and when the queue fills up, instead of dropping the packet is truncated so that only the headers are forwarded to the receiver. This way, no packet is ever dropped, and the receiver has a complete view of who's trying to send it packet, even in an in-cast scenario. Then you have in-band network telemetry, which has become quite popular as well, and this is to give you visibility in your network. And then you have some more like computing-oriented applications, like NetCash, which is in-network key value store to accelerate Memcached. NetPaxos, where you can run Paxos, which is a consensus protocol, in the switches itself, sorry. And then you have a few applications for machine learning application to reduce weights, for example, directly inside the network, because usually when you run machine learning algorithms on clusters of GPU, you're generating a lot of traffic because every GPU needs to know about every computation result by every other GPU. So in this case, we're able to do a lot of the work in the switch itself to reduce that I/O pressure on every GPU. I just have a slide on in-band network telemetry, which is called INT, because I thought that was an interesting application to mention. So what is INT? Well, in INT, every device in the network, which is P4 programmable, is programmed with a specific P4 program that tells the device that for every packet, some metadata information needs to be added to the packet, let's say after the TCP header, for example. So you get your packet, it gets to the first switch. Here you can add some metadata, such as a switch ID. Usually you add like timestamps. The time at which the packet was enqueued at the queue in the switch, the time at which the packet was dequeued. You can also add some information about which flow rules were hit in the switch. And so why do we do that? We do that because if we mark every packet and if we collect the results at the end of the network, we're able to basically get a lot of data, get a lot of information about what happened during the lifetime of the packet through the network. And we're able to answer some very interesting questions, such as which path did my packet take exactly? Which roles did my packet follow? How long did it queue at every switch? And who did it share the queues with? So if you have some traffic which is delayed because there is a queue buildup in one switch, thanks to INT, because every packet is tagged in your network, you are able to determine which packets from which flows were in the queue at the same time as the packet that you're interested in. And thanks to INT, thanks to P4 programmable devices, you're able to tag every packet at line rate and gather a lot of data, look for anomalies, and report them to your network operator. And INT has been like demoed in many conferences before. It's been implemented by many different devices, not just switches, but also programmable network interface cards. So basically, when you have a network doing service chaining, where you have a packet traveling through a fabric, going through different VMs, running in different hypervisors, you're able to add that INT metadata in the switches, in the NICs, in the hypervisor, and you're really able to get like a complete picture of what's happening to your traffic. Another application, as I mentioned, is NetCash, which is an acceleration mechanism for a key value store. So the idea is, well, a typical deployment is to have a bunch of key value x86 servers in a rack with a top of rack switch, and those servers are going to process different read and write requests from the from different clients. This is what happens with protocols like memcached, but also distributed Redis and so on. So the idea with NetCache is to actually keep a dynamic key value cache inside the network, inside the top of rack switch, inside your regular top of rack switch, if your top of rack switch is P4 programmable. So that cache is dynamic. The switch can keep track of which keys are popular at any given time, and it can cache those specific keys. And what's very interesting is, well, usually in a data center class switch, the amount of memory you get, of on-chip memory you get, the amount of SRAM you get is pretty small. So the amount of keys and values you can store is actually pretty limited. But it's been demonstrated that if you can cache n log n amount of keys, where n is the number of servers you're serving, basically you can get some great load balancing across every server, and you can avoid like overloading a specific server if that server happens to have all the popular keys at a given time. If a server has all the popular keys at a given time, then those keys are going to get inside the switch, and the switch can deliver like billions of requests, average requests per second. So, oh, I need to go back a little bit, sorry. Yes, so when we started designing the P4 programming language, we had to come up with some useful abstractions, with some useful building blocks, which can be used by a P4 programmer to express any kind of algorithms they want to run in their network. That abstraction also had to be convenient for compiler implementers, because if you want to convince people to adopt P4, if you want to convince vendors, it has to be easy in a way to implement on their specific silicon. And for our abstraction, we adopted like a switch model, which is called the PISA architecture. PISA stands for Protocol Independent Switch Architecture. And PISA integrates three different basic components. So you have the programmable parser. So unlike OpenFlow with P4, you don't make any assumption as to what kind of packets you're going to be processing in your network. It's up to the P4 programmer to define a programmable parser, which is essentially a state machine in which you specified which packet formats you're going to be accepting in your packet processing pipeline. So this parser takes the form of a state machine. Usually, you have one state for each different protocol. In a state, you're going to extract some information from the packet, and then you're going to take a transition based on the information you just extracted. I'm going to give a very simple example. If you know that your program is only going to be processing Ethernet packets, well, the entry point in your programmable parser is going to be a state, an initial state, which is going to extract 14 bytes from the packet. So 6 bytes of DMAC, 6 bytes of SMAC, 2 bytes of Ether type. Then your parser is going to look at the value of the Ether type field. And based on the value of this field, you're going to move on to extract IPv4 header or the IPv6 header or any custom header you might be using in your program. And I took Ethernet as an example, but really because it's like protocol independent, it can be any type of protocol, even L2 protocol. After your packet has been parsed, we move on to the programmable match action pipeline. So in P4, we reuse the match action abstraction from OpenFlow. And so basically, you're going to take the headers you extracted in your programmable parser, and then you're going to run those headers through a sequence of match action tables, which are going to modify the packet. And finally, we move to the programmable deparser, which is going to take the modified headers, the headers you've modified in your programmable match action pipeline, and it's going to turn those headers back into a packet stream and put it on the wire and append the payload at the end. So PSA in action, I hope the animation is going to work. So the first step is the packet is received on the wire. It's parsed into individual headers according to the parser state machines that you've defined in your P4 program. Those different headers can go through multiple stages of match action. And so what you end up at the end is a set of modified headers. Obviously, from one match action table to the next match action table, you can carry with you what we call metadata, which are some extra fields which are not included in the packet, but which are useful for you to determine what to do next with your packet. And finally, the set of headers goes through the programmable deparser, and your packet is serialized again. Sorry, yeah. So very quickly, the core elements that we have in the P4 language, or as we just saw, the parsers, state machine to decide which packet format your program is going to accept. Controls are used to define graphs of match action tables and also to describe your deparser block. The parsers, the controls, those are programmed using the different types and expression formats available to you in the language, and I think Andy will talk about this. So those components, the parsers, the controls, the blue boxes, those are provided by the P4 programmer. But we have some additional elements in the language. We have what we call architectures, P4 architectures, and P4 externs. So what is an architecture? Well, early on in the life of P4, we used to have, the programming language itself used to assume what your programmable device needs to look like. So we had an old version of the language called P4.14, which came out in 2014, which said, okay, a programmable networking device is going to be a parser. It's going to be two different match action pipelines, one on ingress, one on egress, and it's going to be a deparser. What happened is, working with multiple vendors, working with the P4.org community, we realized that one size does not fit all. We cannot constrain vendors which are willing to use P4 to assume a specific architecture for their hardware. And so we created the notion of architecture so that vendors can define describe exactly what they expect from the P4 programmer. For example, if you have a switch, maybe you have like multiple parsers, maybe you have multiple deparsers, maybe you have multiple programmable match action pipelines which are independent from each other. And all of this you can express in your architecture. If you have like 4 different match action pipelines which are independent in your hardware, you can tell the P4 programmer, which is writing a P4 program for your hardware, that programmer needs to provide 4 different controls, 4 different pipeline implementations, because that's what your box can support. However, we also have architectures for things like programmable network interface cards, programmable NICs, and usually the architecture of a NIC can be completely different from the architecture of a data center switch. And so for NICs, we have a different set of architectures which can be used specifically to program NICs. And so that's the P416 approach, to say the language is going to be agnostic to what kind of hardware you're programming. Basically, we say the vendor is in charge of providing the architecture for their equipment. The architecture defines some interfaces that the P4 programmer has to rely on. You can think of it as like some kind of API you have to integrate with. However, for the sake of portability, we don't just have architectures provided by vendors. We also have some architectures which have been developed by the p4.org community. We call them the portable architectures. We have one for switches. We're working on one for network interface cards. And why do we have those things? It's because we think it's important for P4 programmers who care about programmability, who care about vendor independence, silicon independence, to be able to write P4 programs in such a way that those P4 programs are going to be able to run on different pieces of silicon from different vendors. So these are some examples of architectures that the p4.org community or specific vendors have developed, but those architectures are also open source in this case. So the V1 model architecture is what Andy is going to be talking about afterwards. So in the V1 model architecture, oh, sorry, I didn't move. So the V1 model architecture includes a parser, includes a match action pipeline, includes what we call the TM, the traffic manager, which enqueues your packet, but can also take care of things like multicast. Then we have another match action pipeline, the egress match action pipeline. And finally, we have a deparser block. The simple SUME switch architecture, which was developed by Xilinx for their programmable NICs, only includes one match action pipeline. So there is no egress match action pipeline. And finally, the portable switch architecture, which has been developed by the p4.org community, as kind of like a refinement of the V1 model architecture, includes a programmable parser, a match action pipeline, a deparser, then a traffic manager, and then the same thing again on egress. And so this is how, in practice, you can program a P4 target with your P4 program. So obviously, you start with, you purchase some P4 programmable silicon, and what it comes with is an architecture model, which is provided by a vendor, and a P4 compiler, which is also provided by the vendor. So that P4 compiler is going to be able to take your P4 program and transform it into, oftentimes it's a configuration binary. At least it's the case for the ASIC I'm familiar with. It's also the case for FPGAs, where you can produce some RTL file. And then you're going to load that target-specific configuration binary into your device. And that binary defines what kind of tables you need to carve in your SRAMs, in your TCAMs, and other things, like does your target support counters, meters, and so on. And finally, you're going to have to write a control plane, which is going to be able to talk to those data plane objects you have defined in your P4 program. And this is done using the P4 runtime API. If we have time at the end, we will talk briefly about it. And the most basic functionality you can do with the P4 runtime API is things like adding and removing table entries, just like in OpenFlow, reading stats from counters, configuring meters for rate limiting, doing things like packet in, packet out to inject packets into the data plane and receive packets from the data plane. And on this, I'm going to hand it over to Andy, who is going to talk about concretely what a P4 program looks like.
I can switch it there.
Yeah.
All right. Hi, my name is Andy Fingerhut. I'm a principal engineer at Cisco Systems. I've in a past life at Cisco in early 2000s, I worked on the CRS-1 product where we had a network processor and programmed it in hand-coded Tensilica assembly. So it's definitely a lower level thing, and you had to get right into there in the hardware to understand what to do, how to process packets. So this P4, when I learned about it a few years ago, I jumped in with both feet because it's an interesting opportunity to take something that, I mean, Barefoot's got some amazing technology for taking stuff, taking a programmable device and making it the same or just maybe a little bit more expensive than the cheapest devices that are out there that aren't programmable, versus NPUs that I've worked on that tend to be like 5 to 10 times more cost per port for the same kind of programmability. So I wanted to take a brief break here, or call for questions if anybody had any on the first part of the talk, and see if anybody had anything they wanted to ask. My plan is to go into, oh yeah, there's some microphones here. It might help everybody hear the questions.
Hi. So the metadata that can be carried through the tables whenever you're doing that initial processing, is that something that's completely programmable by the user? Is that predefined? How much flexibility do you have with that?
Sure, good question. So there's the word metadata is used for kind of two slightly different things in P4. One is the so-called user-defined metadata, and this is completely up to your particular program. They're effectively temporary variables that, again, may or may not be copies of things from packet headers. They could be, for example, you might derive a VRF for a packet if you wanted to implement VRF multiple layer 3 tables. That's something that's not in the packet when it came in. You looked up some table, you remembered a VRF, you carry it through the rest of the program. You get to define that if you want. If you don't need it, you don't define one. Any particular target is going to have a limit on how much of that data you can define per packet. So for example, maybe there's the Defino is somewhere around 512 to 1,000 bytes per packet. You can don't quote me on don't file a bug against me if I misquote there, but it's on the order of that size. It's not megabytes per packet, definitely, and it's way more than 16 bytes per packet. Then there's so-called standard metadata, which basically is things that the architecture defines that you don't get to change, but you probably want anyway. Any packet that arrives on a multi-port switch, you pretty much want to know which input port it came in on, because you might want to treat different packets from different input ports differently, maybe a different access control list for different input ports. So that an ingress port is kind of a standard metadata thing that you can't remove. You don't have to use it, but it's there for you to use. And then another one on the output side would be, I want to say the packet should go to this output port, and that's something, there's a standard name in the architecture that tells you assign a value to this, and that's where it will go. Yep. Another question.
It's somewhat related, but in the architectural figures, we see queues at the output, but yes, we don't see it in the input. So I'm trying to understand in my idea whether, to my understanding, whether there's where input queuing comes into place, and presumably can you do some parsing stages and then decide. Well, go ahead.
Let me see if I can jump to one of these slides here. Not too far away, sorry for the, so yeah, there we go. So a lot of the implementations that you'll see this V1L, for example, so what's not shown is on the left side is the input ports, the Ethernet ports typically where the packets will arrive. Parsing and the ingress match action pipeline before the traffic manager. In some implementation, that's a fixed latency function. So in fact, your program over a certain complexity won't fit into a target that has a fixed latency function because there's only so much you can do in a few hundred nanoseconds. Mm-hmm. And so, and they also, many of them have a fixed deterministic rate of packet processing. So 1 billion packets per second or 1.5 billion, something like that for some number of Ethernet ports. And so you're pretty much guaranteed how long it's going to take from the time the packet arrives in the input port before it will get enqueued in the traffic manager. And then similarly, egress processing will take a fixed amount of time and have a guaranteed rate after this packet scheduler has picked a packet to go out on a particular output port. I don't know if that fully answers your question or not.
Yeah, that was great. Thanks.
Okay. Any others? Yeah.
Hey, Andy, can you go to a couple of slides before?
Later or earlier?
Before the metadata slide.
Okay, sorry, I may be going the wrong direction. We'll see.
Probably before, I guess.
Before this?
Yeah, I think so.
Oh, man, we get to find out how many. Sorry,
I think before this.
Okay. I don't know if, sorry, I don't know how many steps we'll go here.
Yeah.
As well
So
as-
you see this log analyze replay, right? So this log analysis happens on the packet metadata that was carried through the pipeline, right?
So in this case, each of those ovals there would be a P4 programmable device that you have, besides doing, let's say, normal layer 3 forwarding or layer 2 forwarding, you'd have the INT, the in-band there'll be additional headers you'd add on at the first switch, update at the intermediate switches, and then at the last switch, before you go to the host won't understand that header if it sees it, so the last switch's job would be remove that extra header and copy it perhaps into some message that goes to a server that is that log analyzer. So typically the log analyzers here would be a general purpose CPU or a rack of CPUs, and the data going there would be in something like NetFlow export packets.
Okay, so this is like well-defined, like if I wanted to see some metadata that I'm interested in, it's like a well-defined where any third-party guy can like tap the packets and read what is going on. Or is it not anything proprietary, right?
So if you have a P4 programmable device, like Barefoot Tofino, like Xilinx's FPGAs that are P4 programmable, you get to pick what's in those additional headers you add onto the packet. So for example, there's things like the timestamp when the packet arrived here, the amount of time it spent in its traffic manager queue, which input port it went on, which output port. Those are things you get to pick and define the format if you want. There is a working group that's defining in-band network telemetry sort of standard header formats because some people want to implement some of these in-band network telemetry features on fixed function ASICs as well as programmable ASICs. And so they want to kind of...
So is this a packet replication that goes to control plane apart from being sent on the data plane?
So anything that goes in the log analyzer would be a copied packet, yeah.
A copied
Something
packet.
like span or NetFlow export, yes.
Okay, so I'll catch you later.
Okay, yeah. Oh, and I'll be available for probably until 7 p.m. or so after the tutorial if folks want to chat or ask additional questions too.
Hi, this is Nikhil from Oracle Cloud Infrastructure. So in, I think, one of the latest slides, you had on the target, you had a differentiation between the control plane and the data plane.
Yep.
So is the control plane an essential component of the target? And does it have to be like some kind of a CPU, or can we like export a, let's say, packet in out?
So, I mean, we're going to focus here a lot on the P4 programming language and the programmable data plane. But, I mean, have you bought any Cisco gear? I don't want to. I don't want to say anything too. I understand customers' pain sometimes when there's most of the bugs are in that control plane code. P4 programs tend to be like for a fairly complex device that does a lot of things in a data center switch. You can specify in about 5,000 to 10,000 lines of P4 code for the data packet processing. But there's nothing in there that tells you how to do OSPF routing. There's nothing that's BGP routing. There's no access control list CLI configuration or management CLI or any kind of SNMP. All that kind of stuff is in the control plane. So the control plane does to be at least 100 times bigger than that data plane, and that's where most of the bugs are. To be negative.
But as you said,
most of the features are.
The whole reason for doing this was to actually move the control plane out and centralize it, right?
So whether the control plane runs locally on a CPU that's near the data plane or in a controller that controls many devices
that's open,
is a not prescribed by P4.
Gotcha.
Yeah. And in fact, the P4 runtime, if we talk about it, is meant to work over TCP sockets, and so can be either local on the same CPU or remote over the network. That's a design choice for whoever operates the network. All right. So what I was planning to do, again, feel free to actually jump in questions and speak up if I don't notice you for a bit, because there's 3 microphones here. I encourage questions during this time if it helps make things clear, and we'll have hopefully time at the end. My next plan was to go through and just kind of dig deep into a small P4 program. We're not going to, if you like those examples of doing Paxos and image network telemetry, no, I'm not going to dive into that. I am not prepared for that today. We're going to do closer to the hello world of P4, not than the in-band network telemetry of P4. Now, I was hoping, Antonin and I spent last week, there is some instructions that I think is on the NANOG site for how to install some software if you want to run these example programs yourself. And it takes, if you haven't installed it already, if you have installed it already, great, and you want to follow along here, that's great. But if you haven't, it's like 1.5 gigs and probably 20 minutes to install if the Wi-Fi agrees. And I don't know how much the Wi-Fi agrees. But there, I will spend a couple of times mentioned here. Yeah, here's the page that you can go to that gives instructions on. I've done this on a Linux machine. You've done this on the Mac directly? Okay, so and both work? Cool. All right, so last week we spent like 1.5 days, 2 days making sure that these examples, the ones I'll mention soon, are up to date and the make files and the README instructions should be accurate. There's a GitHub tutorials repository that you can pull, and you're free to file GitHub issues if you have troubles running the tutorials, and we might be nice and answer. So yeah, if you do want to follow along, these are just some suggestions. First, follow those instructions if you haven't. Even if you have, we updated that tutorials repository Friday last week was the last time we've touched it, and it should be perfect now, and for now. So those instructions will instruct you to install a Docker container. I learned how to do that. I'm a dinosaur. I learned how to do that first time 2 weeks ago. So it'll pre-install a particular version of the open source P4 compiler. BMV2 is short for Behavioral Model version 2. That's a software switch, something like OVS, for those who've heard of OVS, except it's not targeted at high performance or production. It's targeted for debugging your programs and developing your programs and running arbitrary P4 programs. So that's the reference compiler. It installs a binary, precompiled binary for that. And then Mininet is, for those, it's a, I don't know if it's purely Python-based. I think it's mostly Python-based, and it lets you create a bunch of, a collection of virtual switches and hosts in a topology that you get to define in a Python program and create it and let them pass virtual packets between them. But it will actually run your P4 code on each of the switches and let you ping and send various packets between the emulated hosts running in your laptop. So inside the tutorials directory, there's an exercises directory. Don't go there. There's a P4 app -exercises directory. That's the one we've updated and planned for this one here. Unfortunately, it doesn't say on the slides, but that's the one that we've updated. And inside of that P4 app exercises directory, there's a basic.p4 app, which is the first one. And that's a good one to start with. Each of those, there's 3 P4, there's basic tunnel, and then P4 runtime are the 3 exercises that are in that P4 app -exercises directory. Each one of those subdirectories has a README, which is a good place to start. We've updated those, we've tested those multiple times. They should work as stated. And they also contain a make file, which the README tells you which make targets to run at various steps to start the thing up or shut it down or update for the next step. They also contain a main.py Python script, and this program, if I remember correctly, for each one, it's fairly short. You can look at it, but it basically uses some Mininet library calls to create the virtual topology of a few switches and a few hosts. And at the end, for the first couple of exercises, we don't expect you to write a control plane, any control plane code. We expect you to just write P4 code, and we actually write a tiny little control plane code for you that just installs like a handful of table entries. And so don't change that's intended to make it the first couple exercises easier. The third exercise, if you ever do that, you actually get to modify that Python code and install your own control plane entries. But we won't get that far today, I don't think. All right, what else? Yes, and so each one of the exercises contains a P4 program to start with, and the README tells you what you need to update in each one to actually make it work. They often have to-do comments inside the original P4 program that tell you, hey, you need to update things here, but it's a pretty filled in, it's 70 or 80% of what you need, and then you get to do the 20 or 30% to finish it for the exercise. And everyone has a solutions subdirectory, which has a worked out complete answer in case you want to just go faster or see how somebody else did it if you get stuck on something. Yep, and there, yeah, the to-dos there. Okay. All right, so we've seen this picture before. So again, we have a parser on ingress. When packets arrive on the left, there's ingress ports. Packet first goes through parser. There's actually in V1 model a detail we haven't talked about before. The first step it does after the parser is there's an optional control block in the code that I'll show you that we can check checksum. So this is most commonly used for if you have IPv4 headers, there's a header checksum. If it's wrong, you typically want to throw away the packet and not forward based on the corrupted header. That's the place where you do that. Following that, there's the general purpose match action pipeline. That's for the kitchen sink of features that you might want. Layer 2, layer 3 forwarding, multicast decisions, all kinds of stuff. We'll start simpler. Then there's the traffic manager. So typically one queue per output port, or more typically a handful of queues per output port if you want multiple classes of service. And this block is not P4 programmable in most existing devices. There's some early researchy work to consider making this P4 programmable so you can change the scheduling algorithms, but that's give that a year or 2 or 3 before that becomes commercial reality. Today, in most devices, that's just something that tells you how many queues it has per port, and maybe you can do weighted round robin with a priority queue or something, strict priority queue, something like that. That's not P4 programmable. You get to tell it in the ingress pipeline which queue you want to go to, which output port you want to go to, but how the scheduling is done is not specified in your code. In the egress pipeline, after the packet's been scheduled to go out, then there's the general purpose stuff in the egress. Why would you have egress processing? The most common reason would be you would have things like you want to put a timestamp on the packet just before when it left the device, or the queuing delay that I experienced in the traffic manager. You don't know that until it's been scheduled. So those kinds of things you don't have enough information to do it until that point. Sometimes there's multicast replication where you want to do something different on each copy. That's the place you do that. Just before the deparser, there's a way to update checksums. So again, if you have IPv4 header checksums, you'd want to update them there if you've modified anything in the IPv4 header. And then the deparser just collect all the modified headers and write them out. Okay, so I mentioned earlier in one of the answers, there's the user-defined metadata, then there's typically what's called standard metadata. Standard metadata is the stuff that the architecture defines for you, predefined, you can't remove it, and some of them are more, I'm just going to focus on the most important ones, which I may have even mentioned before. The ingress port, again, I did mention that one. Every time a packet arrives, you typically want to know where it came from. Maybe you'll ignore that in your packet processing. It depends on what you want to do. You might want to use it. Almost every packet you'll either want to drop, or if it's unicast, pick which output port it's going to go to. And the egress spec metadata field is where you'd store the output port in this V1 model architecture. And that one should be written in your ingress code because you need to pick the output port you want to go to before you get to the traffic manager. On the egress code that you write, you're not allowed to change you already decide which output port. It should be decided on ingress. By the time you schedule the packet, it's just before it goes out the output port. You're not going to change it to another one and mess up the packet scheduler. That would mess up the packet scheduler. So there's an egress port that tells you what's already been decided for where it's going, and you can read it, but you shouldn't modify it. There's a bunch of others there, and I'm not going to go through those, but these are the ones enough to get started with. Okay. All right, so here is a template of what, in fact, so this might look like a little bit of boilerplate, and it is. I mean, this is more boilerplate than your Java Hello World code is. Those you can write in 3 or 4 lines of code. This is definitely more, and what I do is every time I start a P4 program, I just copy an existing one, delete the contents of the bodies of these various blocks, and then use it. Because it's, yeah, I don't want to type those 50 lines of code again. There's plenty of example programs to start from. Anybody write C, C++ code before? Java? Any of those? So the way I've described P4 Delaplane code, I'll stand on one foot, which I'll probably fall over if I actually try it, especially standing on this thing, is start with C or C++. If you start with C++, remove classes and exceptions and all that other stuff. Get it down to C. Now, go further. Remove loops. That causes some people's eyes to bug out. This is not a general purpose programming language. You do not want to write arbitrary programs with this. This is very focused. Removing loops is a big eye-opener, like, wow, that's not a regular programming language at all. Remove pointers. Remove malloc and free. No general purpose data structures like that. Everything's fixed size, basically. You might think this is crazy. Why would we make a programming language like this? These are targets. Some of these targets can process packets in a single chip device that costs, maybe $1,000, $2,000. Same kind of thing you get from Broadcom, same kind of cost per port you get at, 5, 6 billion packets per second. You're not going to do that on general purpose CPU. I mean, that's how fast you can, several cores, 2 cores maybe on a 3 gigahertz chip can maybe do 6 billion instructions per second. This is 6 billion packets, which are doing a lot more than you can do in one instruction stuff. So loops and, you can do a lot. You can do a lot in these things. And most data plane programs are much simpler than your control plane programs. So it's really focused for that job. Okay. So there is a section, let's see how the highlighting goes here. Oh no, okay, I'm pushing the wrong button, that's why. So in this template, we'll start at the beginning here. There's an include core.p4. That is, it's a handful of definitions that are in all P416 programs. It's not very big or terribly interesting. There's include V1 model, so Antonin mentioned how there could be multiple different architectures for a P416 program. V1 model is the one we focus on today. He mentioned PSA. You could have a different architecture for a programmable NIC using P4, for example. So they would typically have differences between them. And you'd include a file for that. Typically, after that, you will define your own headers. So a little mind-boggling thing in this protocol-independent part of P4. I mean, yes, if you have a device that has Ethernet ports on it, you're pretty much always going to parse an Ethernet header first because that's what's going to come in off the wire. But after that, it's really up to you. I mean, you could write a P4 program that doesn't even extract the Ethernet header, but it's going to extract whatever bytes are coming in first off the wire, which will probably be formatted as Ethernet header. But it's really up to you what these headers contain, which is the advantage of flexibility, the disadvantage of, well, why doesn't it just do what I want? If I want Ethernet, IPv4, and TCP, well, it's easy to copy. The definitions for those kind of headers is very simple, can be copied from a lot of open source P4 programs. They're not difficult. And then you also typically define some structs, like C structs. They're just basically collections of either multiple headers that you want to go together, group together for your packet from your part that you are interested in for the packet, or the user-defined metadata are typically grouped together into these structs. So after that, the blocks here are going to follow along with that V1 model left to right path of parser, checksum, ingress processing, egress processing, checksum update, deparser. And so there's a separate block for each of these. Each one has a set of parameters in parentheses there. They look kind of like, these are kind of like parameters to a function in C. These that you see here, these particular parameters, don't touch them. These are part of the V1 model architecture. If you remove one, the program won't compile. If you add one, the program won't compile. Inside of these blocks, you can add user-defined metadata and other things you want. Inside of those types, like that, the one that's out headers. Headers is a type defined typically earlier in your program. You could define the contents of that header struct. As many headers as you want will fit. That metadata struct, you can add or remove user-defined fields there all you want, but don't actually remove the metadata type, just what's inside of it. And then the standard metadata one is the one that I showed you that predefined for this architecture. So don't change these parameters other than customize the headers and the metadata types for your particular use case. Just leave the parameters of these things as they are. Checksum verification, again, this is where we do optional checking of received checksums. Ingress processing, egress, checksum update, deparser. Now, you notice that there are names like my parser, my verify checksum, my egress, and all these names. Are those baked into the language? No, they're not. What is baked into the architecture in the V1 model at P4 is that at the end, you need to define this V1 switch name like this. And then those 6 parameters to it are the names that you want to plug in for those things, a parser, checksum, ingress, egress, and so on, in that order. So you can change that name, my parser or my verify checksum, to whatever you want. Just change it where you need to define it and change it at the end of the program if you want to. There's no reason to change it in these example programs, but That's where the name correspondence is coming. And then that thing has to be called main at the end. I'll take a brief breath for any questions. All right. So with that skeleton, we'll go with probably the simplest program that does anything anywhere near interesting. And so probably the most interesting thing you can do with customizing that template with just 5 lines of code is, I receive a port on packet 1, send it out packet 2. Don't change it at all. If I receive it on port 2, send it out packet 1. Don't change it at all. If it comes in on any other port, any guesses what this program might do if a packet comes in on port 3 or 4 or 5 if it has one? Dropping it would be a good guess. If you actually try it, it's a little bit weird, but the V1 model architecture, there's that egress. So we noticed that this program says, so if the standard metadata.ingress port, that's the standard metadata I talked about, the ingress port, if it's 1, set the egress spec to 2. That's where the output port you want the packet to go to. Otherwise, if the ingress port is 2, set the egress output port to 1. If the ingress port is 3, it won't execute any code, and the packet will go to the traffic manager. It turns out that this egress spec variable is actually initialized for you to 0 before it ever starts your ingress code. And it turns out that in the V1 model architecture, that means it will go out port 0. So kind of an odd, weird thing in the V1 model architecture. It's just kind of a nitpick thing. In some other architectures, they actually define it so that the default is drop, and you have to actually clear a drop flag or do something else to prevent it from being dropped. That's just an oddity of this open. I think this V1 model open source architecture is the only one that has this kind of weirdness. Most of the other ones I've heard of default drop. Okay, so that's the first complete, I think, just about complete P4 program here. It doesn't define the header content. In fact, notice it says struct metadata, left brace, right brace, struct header. This is actually a complete P4 program that just has it doesn't parse any headers. Like, there could be an Ethernet header here and there, it'll just ignore it. It doesn't matter if there's an Ethernet header there or not. It'll just, I don't need to look at the header to do this function here. I only just need to know which import port it came in on. So you might wonder, if it's not looking at any headers, how does it know what to send out? If it's not sending any headers out, it's basically whenever the parser stops at a particular point, whatever headers you tell it to parse, it remembers, oh, I stopped here at this byte offset from the beginning of the packet. And this one, it'll stop at byte 0 and just never. The deparser basically says, okay, spit out these headers, maybe modified, but then append to it everything that the parser didn't look at, which in this case is the complete packet starting at offset 0 bytes. So that's why this won't modify the packet contents at all. Okay. All right, let's go a little bit fancier than just hard-coded receive on port 1, send out port 2. That wouldn't be very useful if you had to modify your source code every time you wanted to update. If you just wanted a cross-connect device, like in a lab that just forwarded packets, everything from this input port to this output port, I've set up those devices in test labs and things like that. But typically there's a CLI or some GUI or something for configuring that. Well, let's make it configurable at runtime without having to recompile our program now. So a P4 table that we see here, named forward. For every table, we'll have several slides talking about the details of them. You define a search key. What about the packet or the standard metadata or the user-defined metadata? What fields do you care about searching as the key in a table and seeing if there's a matching entry or not? In this case, it's just the ingress port alone. And we say it's exact. So we don't care about longest prefix match or ternary TCAM matching. We just want to know, is the ingress port exactly this value installed in the table or not? And there's a list of actions defined. The actions names are set egress spec and no action. No action is a predefined one that just no op, don't do anything. Set egress spec is defined a few lines above that red box. And it basically just assigns a value to this egress spec metadata, the one that says where the output port is. And notice it has a parameter, bit 9 port. And any parameters to those actions of a table like that come from the control plane, as well as the keys. So the keys for which ingress ports should be matched on and which output ports should go to come from a control plane API after you compile this program. They're not anywhere in this program. You won't find them here. So you load this into a device. It has an empty table. If you search on an empty table, it does the default action of no op. That'll actually send it out port 0 again, like I mentioned earlier in this case. But you could also make the default action drop if you wanted to. And then there's a size of 1,024 entries. So we can up to 1,000 entries. And the control plane can later at runtime add and remove table entries to this table dynamically while the device is running and while it's processing packets. And then we see sorry, I should have gone there. So in this particular case, if the control plane chose to add these two table entries that we see here, it would behave as the previous program does. But the control plane doesn't have to pick these table entries. It can choose to add other things. Okay. So unfortunately, I just have the slides here. I'm all ready to do a live demo, coding demo. I've got the code all loaded up on here. But I'm just going to describe to you what that would look like a little bit, and feel free to do it on your own right now or at home later. You can play along. Again, the readmes in those that basic.p4app directory is pretty detailed on what you need to do, and there is a solution already in there. So let's see what I need to say here. All right, so the goal of this first exercise is we want to do very basic router-like, I'll say, functionality. It's not even a full RFC compliant router at all, but we'll see what it does do. It'll parse Ethernet and IPv4 headers, if there's an IPv4 header there. Look up the destination IP address of IPv4 packets, update source and destination MAC addresses, decrement at TTL, set the output port, and then whatever modifications were made to the Ethernet header and the TTL and the checksum will get deparsed and sent out with the packet. And again, after that, as I mentioned, anything after the IPv4 header is parsed is just carried along for the ride. So there's this basic.p4 program that is in that tutorial's p4app exercises, basic.p4app/basic.p4 is a starting point. And it has a couple of to-dos in there, and the parser isn't written for you yet. But it will look a lot like some examples I'll show you soon. The topology that when you run make run, as it says in the README, it will actually start up a new Docker instance at that point. And inside of that Docker instance, it will run Mininet. It'll run that main.py script, which will invoke some calls in the Mininet library that creates 3 virtual switches and 3 virtual hosts with these names and these IP addresses. And then it will take whatever your basic.p4 program was, compile it for you, report any errors if there were any, and then it will stop and exit if there were errors. But if there weren't errors, it will load that p4 program up into those 3 switches. And then it will, at the end of main.py, it'll install I think it's 1 or 2 table entries and maybe 3 table entries into each of these 3 switches that if you've written the program correctly, it should let you forward packets and ping between these things. Yeah, and so part of the exercise would be to try to send a packet from H1 to H2. There's additional Python programs, send and receive.py, that you can run receive on H2 and send on H1, and anything sent by H1, you'll get a detailed packet dump of the contents of the packet received by H2 and see if it looks like what you expect. Okay, so let's start going through more details of the language that we've talked about yet. So there are several basic types that you'll see all the time in almost every P4 program. One is bit, and then angle brackets, a number. That is an unsigned integer with a fixed bit length. So that's very useful for, you want bit 48 for an Ethernet MAC address, bit 32 for an IPv4 address. You often want to specify in headers, and even for headers especially, you need to follow the RFCs or the IEEE standards for the sizes of fields and things like that. But even for user-defined metadata, you will typically define specific bit widths for them, and those you just kind of decide. Why would you want to make something bit 9 instead of bit 32 like you would just do int? Some of these targets, that user-defined metadata is a pretty scarce resource, and so if you just say, oh, I'll just let my VRF be 64 bits, you're wasting potentially, 56. If you only do 256 first, 8 bits, you're wasting 56 bits of the user-defined metadata that might be useful for something else if your program gets large and complex enough. So there's a lot of things where you'll think like a hardware designer, a little more of economizing on bit space sometimes. There's signed integers, 2 complement signed integers. You can define with int. And varbit is a type that is typically only used in headers. So for example, if you have an IPv4 header that has the 20-byte base header followed by optional options, you define that. Often, if you don't care what the contents of those options are, you just want to carry it along through the ride, you'll define a varbit field at the end of your IPv4 header, and then you have to use special parser statements to say, calculate the length of that for it and tell it how long it will be. We won't be going through that in detail, but those are described in other example programs and the P4 language specifications, how they work. Header types contain any mix of bit, int, and var-bit types you want. Most implementations say you can only have one var-bit field at the very end, the last, but all the ones we'll see will just various bit size fields. The byte-aligned part here, most implementations will restrict your headers, not the individual fields, but the total length of all the fields to be a multiple of 8 bits, just because I don't know any RFCs that define headers that aren't a multiple of 8 bits long. It's a reasonable restriction on many implementations. Every header in P4 starts out, there's a hidden valid bit for every time you declare a header. So when your parser starts, all your headers are invalid. And then as you parse the headers, they become valid, the ones that you've seen. And then during your code, you can actually set them valid or set them invalid. So if you want to do tunnel encapsulation code or decapsulation code, you can actually add and remove headers at runtime later in your code. And just like all the headers are, like say, are invalid, most of them that you'll get will become valid during your parsing. The first example program, you won't need to tweak that except through parsing, but the capability is there. Okay. Don't think there's anything else I need to say there. Let's see. So other useful types, again, so struct you'll see in most programs typically just as a grouping. If you want to have one or more user-defined metadata fields, you'll group them together in a single struct. There's no valid bit for structs. They're just pretty much like C structs, except don't count on them being particular formatting in memory or anything like that. There's no pointers, so you can't muck with pointer arithmetic and things like that anyway. So structs are just a grouping mechanism, really. Header stacks are not needed for the example, but just to let you know that they're there. They're useful for things like if you have an MPLS label stack. It's useful to have an array of headers type for that. And then header union just is like a C union. It says like this header or that header or that header, but at most one of them can be valid. So in some cases, if you're trying to optimize for space, let's say you might want to say, I know I'm going to have an IPv4 or an IPv6 header, but not both. I want to use a header union to explicitly tell the compiler that it only needs storage for one of those. Okay, so we're going to actually look at the first example parser here, the exact lines of code we'll need to actually parse some headers as opposed to the previous program which parsed no headers. So let's see, every parser starts in a unique start state, named start. That's hard-coded in the language. There's an accept state and a reject state for every parser, again, hard-coded names in the language. And then you get to define as many other parser states as your target will let you write if you want to add more. Very often, we'll see that you'll typically have one separate parser state for each header you might want to extract from a packet or get from a packet. But you can actually extract multiple headers in a single parse state if you want. That's a detail. You'll always start in the start state. Typically, you'll go until you have one or more headers, and then you'll go to the accept state. But you can also reject if there's some kind of bad error or something like that you found in the packet. Up at the top here in the code, we see that from core.p4 part, extern packet in. Packet in is a type that we see down about halfway down the page. Parser, my parser. Packet in, packet is one of the arguments to the parser. Packet in is a abstraction. It's just the sequence of bytes that came in off the wire from the very first byte, which would be the first byte of the destination MAC address for an Ethernet port. It defines a few methods. Extract is the only one we'll be using here, but there's ways to skip over parts of the header or look ahead or extract variable length fields. But the most common thing we'll see here is extracting out fixed length headers. So the parser we see down below, in the start state, the parameter called packet, we call the extract method on it. Every packet at the beginning of parsing has a hidden cursor that you don't have to maintain yourself. It's maintained by the runtime. Starts at offset 0 bytes into the packet, and every time you do an extract, it says, okay, what's the size of that header.ethernet field? Well, it's 14 bytes. So copy the next 14 bytes during offset 0 into that header, make it valid, and now the hidden offset cursor will be at 14 bytes from the beginning of the packet. And then we go to transition accept. We're done parsing. In this particular program, we only care about the Ethernet header. We don't care about what appears after it. All right. And again, yeah, this is here on the right. All the headers start out as invalid. All the standard metadata and even your user-defined metadata is initialized to 0 in the V1 model. So you don't have to explicitly do that in that model. There are some targets where you might need to initialize it, but not in this code. All right, so that's enough for one header, but let's do 2. Let's go to the next. So state start will transition to parse Ethernet. Just as before, we extract out the Ethernet header. If there is one, it'll advance the cursor 14 bytes into the packet. What we want to do next will often depend upon what's in the ether type field. And that if you're familiar with the destination MAC, source MAC, and then a 16-bit protocol or ether type field, it's 0800 hex. If it's an IPv4 header following it, and some other hex values for MPLS or IPv6, things like that, we'll just do IPv4. A select statement is very much like a C case statement. We give it an expression to branch on, in this case, the Ethernet ether type field. And you don't need, unlike a C or Java, you don't need explicit break statements. Everything, there's implicitly a break after each one of these. That's a mistake you can't make here. You give, the expressions are typically a constant. We see the OX800 here. And the parse IPv4 is the name of another parser state to jump to if you take that branch. So the parsers are very often, in these select statements, you can't run arbitrary code in each of those branches. You can do some fairly arbitrary code before the transition select, but once you get a transition select, it's basically just picking which state you're going to jump to next. That's all that's left to you. And then the default is just saying stop, and don't, if there's no IPv4 header, just stop parsing with the Ethernet header. You can also put like ternary masks in those things if you know that some value, and if you only care about the upper 8 bits of the ether type and the least significant ether bit, there's ways to do value masks in those branches as well. Okay, I think I've mentioned, so this is where I would switch to live video and model in front of you and tempt the demo gods, but instead I'm just going to remind you that if that tutorials directory, not the exercises directory, p4app-exercises / basic.p4app is the first one. Look at the README there and follow its instructions. You're welcome to do it now if you want, but I'll be saying such interesting stuff I don't think you want to. Yeah. Maybe. We'll see. All right, so that's the parsers. Let's get to the controls. They look a lot like, and they work a lot like C functions, no loops, again. Inside of each one, you can declare local variables. You can any tables you want to create need to be inside of one of these controls. So every table is either for ingress or it's for egress or it's local to some other control. You can actually, like C functions, you can have your ingress control call another control, which can be useful for if you have a big enough P4 program, you might want to declare subroutines. So they would define them as separate controls. And you can instantiate externs, things like counters and meters or policers, depending on what you want to call them. And every control has all of these things, these local variables or tables, followed by an apply block, which is kind of like the main or the actual code execution sequential control flow of that control. We'll see an example in a moment. Represent all kinds of processing that are expressible as a DAG. DAG is I didn't make these slides, but directed acyclic graph. Don't worry about that. The definition of P4 is that whatever you see in your code, the semantics are, it's as if it were executed sequentially in the order of the statements that you write, just like you would in a C program. Can a C compiler reorder your code if you turn on optimization levels? If it's, and yes, it can, which is nasty if you try to debug that stuff at runtime sometimes if you're looking at it. Now, but what is the C compiler supposed to do? It's supposed to generate object code that works as if you executed your C source statements sequentially in the order they're given. Same thing for a P4 compiler. It's allowed to optimize, reorder things if it's, as long as it matches the original sequential order. All right. Go on to the next one here. All right, so here's an example of a simple control. We've seen another similarly simple one, but let's suppose instead of all packets on 1 go out 2, all packets on 2 go out 1, suppose we do something different. Packets come into any input port. We want to swap the source and des MAC address and send it out the port it came in on, a reflector. That's pretty simple behavior. And we can do it with just a few lines of P4 code. So assuming that we've had the parser we saw earlier where we parse the Ethernet header, that Ethernet header, you can pretty much assume, if you get an 8-byte packet, you're probably going to drop it, but let's assume we always have a 14-byte header that came in. It will be in this header.ethernet header. We're going to create a temporary variable, bit48 temp. We're going to use that to hold a copy of the destination address from the Ethernet header. We're going to assign the source address copied into the destination address. We're going to assign into the source address that saved destination address from temp. And then we're going to set the egress spec, the desired output port, to be the input port, the ingress port. So there you go, four assignment statements and a temporary variable gets you a, you don't want to spend $2,000 for a device that does only this, but here's something you can start with to say, look, Ma, it did something that I made it do. There are also actions. So actions are most commonly used, and we'll see examples in a moment, of things that the side effects of matching an entry in a table. But it turns out you can actually define an action and just call it directly from your code as well. Sort of like another, you can do it with controls, you can do it with actions. So here we see an action defined called swapMac that does 3 of those assignment statements that we just had in the previous example program. And it has 2 parameters, the source and destination address of the Ethernet header. They're declared as in-out, meaning they're logically, it's as if they were copied in, the caller parameters are copied into the parameters here. You can make local modifications to them, and then they're copied back out to the caller. So we see this call to swapMac down there in the apply block, which does the same thing as those first 3 assignment statements, and then it sets the output port to the input port. So just a different way to write the same functionality. And actions are just a way of potentially naming and composing, naming certain groups of functionality. Let's see. Yeah, parameters can have types in it. So there's types, the directions are in, out, in, out. We'll see an example where there's no direction there in the next slide soon. Assignment statements have some of the operators you're used to from C and C++ and Java, like addition, subtraction, bitwise, and, or, XOR, negation, shifts left and right, and then equals, not equal, the usual operators on arithmetic kind of thing. Now, a P4 target is allowed to implement multiplication and division, but believe it or not, a whole lot of network stuff. I mean, I've worked on, like, we to make the chip smaller, we ripped the multiplier and divider out of a little RISC core and use that for a network processor, because you just usually don't need multiplication and division. And if you need them for powers of 2, you got shifts. So there's a whole bunch of data plane algorithms you just don't need multiplication division for, and for area and cost reasons, the language doesn't have those. If you really, really want that, you can actually implement, if you really need it, you can actually implement a table that will give you approximation, multiplication, division. But you'd have to really want it to do it. Try to do it with shifts and adds if you really, really need it. There are choices, but yeah, a lot of data plane algorithms just don't need general purpose multiplication division, nor floating point. There's also bit slicing operations if you want to just extract out a few bits from the middle of an IPv4 address, and you can concatenate fields together. Bitwise concatenation. All right, tables. Tables will often be a lot of the code you see in a P4 program. So, as we saw in the earlier example, each table has a search key. It could be 1 or more fields you pick either from the header or your user-defined metadata, or the standard metadata. They specify a list of possible actions that table might take if an entry is matched. You get to pick what that list of actions is. And there's some other optional properties that could be there, like a size, maximum number of entries you ever care to have, a default action. If no entry matches, what should you do instead? You might want no op, but you might want to drop. You might want set the default verb to 0 if it's no match, something like that. You can optionally specify static entries in your program, like the control plane can't change them, it's always going to be this. That's just maybe a shorter way of writing a long if then else chain. Each table contains 1 or more entries. It's actually 0 or more entries. There's a slight correction here. When you start up a typical P4 program, all the tables will have 0 entries in them. It's up to the control plane to choose to add them if it wants. Every entry you add, the control plane gets to pick what the values of those key fields are. If they're exact match, you just pick a value. If they're ternary, you pick a value and a mask to match on. If they're longest prefix match, you pick a value and a prefix length. So the control plane picks those when it adds entries into the tables. And for each entry you add, if there's 5 actions defined for the table, the control plane gets to pick one of those 5 actions. If there's only one, the control plane doesn't have a choice. It has to pick that one. So the P program restricts what the control plane's allowed, what kind of actions it's allowed to do for each given table. And the action parameters, if they're directionless, they don't have in, out, or in, out on the action parameters. So they call them directionless in P4. That means the control plane picks what those parameter values are at run when it installs the table entry. We'll see an example in a moment to clarify that. All right, so let's go through details. I think I've said some of this, and I might go here quick. So the control plane gets to install the entries. And while packets are being processed, a particular packet comes in. On the left, we see a packet coming in, and we've color-coded some of the header fields or the user-defined metadata fields that are pieces of this data we know about the packet that are coming through and being processed. The P4 programmed device is responsible for extracting out those fields that you picked for that table, combine them together into a lookup key, and send them to whatever the implementation of the table is in that device. On a device like Defino, there'll be a bunch of TCAMs and hash tables. Hash tables are good for exact match, TCAMs are good for ternary and longest prefix match, and there's a few other hardware implementations of those things. And FPGA might do it similarly. Software implementation, again, differently. But however the implementation does it, it's supposed to look up that key, see if there's any matching entry. For ternary and longest prefix match, there's multiple entries might match, but you have to specify priority. For longest prefix match, it's the longest prefix. For ternary, you get to specify every time the control plane adds an entry, you have to specify a numeric priority, and only the first matching one is relevant for that packet. Any later ones that match are ignored, like for a normal hardware TCAM. If there's a hit, then the control plane has also installed the action ID, just usually a numeric value the compiler picked to encode that name of the action. And the action data is the parameters of that action that gets stored into the table as well. If there's a hit, and if there's a miss, the control plane can also typically configure a default action. So in your P program, you can either say the default action is no up or no action or drop. Some tables you might want to say, this table's always going to drop, and there's a way to say const default action, and that means the control plane can't change that default action of the table. But if you don't say const default action, you can specify the initial default action for that table. The control plane can later say, oh, I want to change the default action of the table to drop or no op or any of the actions that's allowed in the definition of the program. If you don't want that to happen, then just make it const and it'll always be fixed. Whether there was a hit or a miss, the action and the action parameters are chosen for that, the one highest priority matching entry or the one matching entry or the miss, and whatever that action contents are then executed for that packet. Whatever assignment statements you typically have in there will just be executed sequentially, and the action is now done, and that table is now, the application of that table is now finished. And then any modifications made to the user-defined metadata or headers will be remembered for the packet and passed on, and now you do the next table if there is one, or if statements, whatever else is in your code. All right, so one example that may be familiar, so if you want an IPv4 longest prefix match table, no VERFs here, just IPv4 destination address lookup only. You would specify a key, which would be the IPv4 destination address. You'd say it's a longest prefix match type, not exact. And let's say you had actions like forward the packet to this output port with this destination MAC address, or drop, or nothing. So this shows in the bottom left here a possible configuration that the control plane might have installed for these table entries here. And if it was the forward action, then you need to specify what the new destination MAC address is and what the output port is. That's something that would come for your parameters of your action in your P4 program. It's not hard-coded in the device. So let's see what the source code for this particular table would look like. So the key there, header, IPv4 destination address, LPM is just an abbreviation for longest prefix match. I mentioned ternary and exact. There's some targets will implement a range, min-max range as well. Those are typically the only ones you'll ever see, but targets are free to implement their own custom ones if they want. We have 3 possible actions: the forward, drop, and no action, a size of 1K entries, and a default action that's initially the no op. So that slide didn't mention the implementation of like what, it gives the names of the possible actions, but those actions need to be defined in your source code earlier, just before the table. I mean, anywhere before the table, but not after. I mentioned these match kinds earlier. Yeah, exact ternary, longest prefix match in range. I've never seen anybody implement regexp in fuzzy, as shown in the bottom example, but somebody's getting creative on other ideas, possible ideas. All right, and so here's some example, at least the bodies for this. So the no action is expect empty. Drop, there's a special mark to drop built-in action in the V1 model that's defined in that V1 model.p4 header file that you can call. You might wonder, why do you have to make an action drop if you just, why can't you just say mark to drop? It turns out this mark to drop is like a primitive built-in that you can't list as one of the explicit actions in a table when you define it. You have to have a user-defined action with a name. Minor weirdness, but easy to live with once you know. And then the action IPv forward, again, we see no in-out or in-out directions on these two parameters, destination address and port. That's because they are picked by the control plane when it installs table entries. They're not things that you supply when you call. When you apply the table, you don't give name values for those names. They're given by the control plane when it installs table entries. Okay. And then once you've defined a table, before the supply block at the end of the control, you can call a table, apply a table by giving its name .apply method. And the apply is included bundle up in all of it, create the search key, search for it, find the matching entry if there's one, otherwise the default action, execute that action. When all those things have been done, the apply is done, and it goes on to the next statement in your apply block. Okay. I'll take a deep breath there for a moment. If anybody has any questions, we're getting there. A lot of stuff there, I know, without live coding.
I have a question.
Yeah.
You may have covered it already.
That's all right.
Is it possible to do a T function so that you can both do the action and then T off and take a copy elsewhere, so you both do the action?
So for example, you want to receive a packet, send it out, do some sort of standard normal processing, but then
Sure.
take a copy of the packet and do something
Copy
different
and
with it?
send it somewhere else.
Yes. So there's no examples of it in the example exercises that we've given you. There is,
Can be done.
the name to search for would be clone.
I saw clone and I
Yeah.
was sure.
Sometimes it's also called mirror. So there's different names. Mirror or clone are the two most common names used in P4 architectures for that operation. Their operations are, so basically if you look then include v1.p4, there's a definition for a couple of clone functions. And I won't get into maybe ask afterwards if you're curious of the details, but yeah, basically it's a way to say, keep going, but remember that I wanted to clone a packet. When you get to the end of this ingress or egress processing, do the normal thing with a normal packet, but also make a copy that starts ingress over again, or starts egress. I think it starts egress with a separate copy. Yeah, so multicast replication, you can specify an ingress to say, I want the packet, the traffic manager to create, go to group number 17 that my control plane is configured, and the control plane is responsible for saying, oh, that should go out ports 2, 5, and 28, and the control plane can change that for the different multicast groups. Cloning is something you can specify, and the control plane gets to configure which output port it gets copied to by default. Cloning, and then there's options for recirculating a packet. Oh, I decided I want to do more on it, start over with ingress again. So there's a few special operations like that, which we won't cover in detail, but they exist. Any other questions before I go on? We're getting close to the end of time. There he is. Okay, he didn't abandon me. No, it's all right, don't worry. I think I'm going to fill out the rest of our time here. Okay, any other questions? All right, so we're pretty much done with this example program. Deparsing is one of the least interesting parts. Deparsing is basically a sequence. Almost every one of them looks like this. It looks like a sequential packet.emit and then a name of a header. What does that do? Basically, in order, it will say, is the valid bit true or false for this header? There's a hidden valid bit for every header. If it's true, take the copy of the contents of that header as it's been modified earlier in your program. So it may have been modified since you parsed it, it may not. If it's been modified or not, take its current contents, if it's valid, and copy it to the output packet. Again, there's like a cursor that starts at a buffer that's created the packet. Copy those 14 bytes out, and now go to the next emit statement if there is one. If there is that header valid? If so, copy it out. Once you've done all the emit statements in your deparser code, then whatever the parser didn't parse, that tail of the packet, the payload, is copied onto the end. So deparsers tend to look pretty like you read your parser code and you pretty much just, whatever I could parse, just emit them in that order, or in order that they could be parsed in. All right, so this is where I would do a coding break. But again, I'll just mention the README files are up to date, and I will bet $1 that they're correct. Don't everybody bet me simultaneously. I don't know if I can cover that today. Not with what's in my wallet. If you all find a bug, no, I'm not going to offer to pay you all $1. All right. This next, so that gets you through the basic.p4 app is the first example. The second example is called basic.tunnel.p4 app. It's a sibling directory. And I'll just describe it here a little bit briefly, but it's basically like now you need 2 or 3 tables instead of just one, like the first example is enough. I'll describe what the desired functionality is. And it's you know, the first time you do it, it's certainly bewildering and confusing. What are all these things? But again, there's a starting P4 program with a few to-do comments in it that say, you know, fill it in here. It's a little bit more work and thinking than the first example, though. So the idea here is let's create a custom tunneling protocol, not defining any RFC at all. If you've got a P4 programmable device, it shouldn't matter if there's an RFC for it or not, as long as it's, you know, simple enough. And this one definitely is. So we're going to define a new header type, mytunnel, and it's going to have just 2 fields in it, a protocol ID. So it'll be like the Ethernet protocol ID, a 16-bit field that would be 0800 for IPv4. So that way you know that when you install this new, so there'll be Ethernet. Optionally, there'll be this mytunnel header and a packet's coming in. It'll have, and then it'll specify what the next header is after that, maybe IPv4, v6, whatever. And then, but a separate field besides that protocol type would be a destination ID, some made up, you know, a custom made up number for each host that you want to send it to. So it's like an MPLS label, but this is simpler than MPLS even. Just an example to get your mental juices flowing. And then we want to modify the P4 program to say, if this mytunnel header is present, ignore the IPv4 header completely. I don't care what the destination address is. I'm going to forward based upon that destination ID that's in that mytunnel header. If there is no mytunnel header, and there's an IPv4 header, now look at it, forward based on that, like in the first example. So in a more, the third example, which I won't even describe really, but other than to say that it has a P4 program already written for you that does something a little bit more like what a real tunneling protocol would do, which is the first hop switch adds the tunnel header, intermediate ones forward based on the tunnel header, the last hop one before the host removes it. This example here, it doesn't add or remove it. It just, if you receive it with there, forward based on it. If it's not there, ignore it, but never add or remove it. So this is a stepping stone to a full tunnel protocol implementation. I'll just mention here the basic to-do list, but again, the README and the to-do file have, in the basic tunnel.p4 app directory, contain copies of all this stuff. But basically, the kind of thing you'd want to do is you want to define a new header. You've got Ethernet, you've got IPv4, you need to define your new custom tunnel header. And there's a header struct that basically has a collection of all the headers you might parse. You want to add an instance of this header to it. Just to mention, so just defining a header type is like defining a C struct type def. It doesn't declare any storage, it's just a format. So you have to actually have something in a struct that's one of the parameters in that user-defined metadata to actually create storage for it, for each packet. You'll need to update the parser code so that when it's Ethernet, if it's 0800, it's v4, but if it's some new custom ether type that you get to pick, or the exercise actually says, please use this value because the control plane is the example packet generators are set up to use that value. Parse, transition to a new state that extracts your custom tunnel header. And from there, you'll want to maybe parse an IPv4 header afterwards. You need to define a new table that matches on that destination ID in that custom tunnel header, and forward the packet based on that and ignore the v4 header in that case. So you can have if then else statements, as we saw in the first example in your ingress and egress control blocks. So you can choose to say, oh, if this tunnel header is valid, apply this table. Else, if the IPv4 header is valid, apply this table. So some of the tables can be completely skipped for packets depending upon other conditions. Let's see. You'll need to update the deparser to emit that tunnel header so it doesn't get removed. And then in this case, the add forwarding rules, there's a main.py script like this one that will install control plane entries for you in the second example as well. So you don't have to. You can look at it, but shouldn't need to update them for that. But if you want to see how it's done, it's in that Python script. Oh, and this is just a picture of what the topology looks like for this one. All right, that's where there would be a coding break if we had more time. But let me just mention a few, what somebody who wrote this slide thought were frequently asked questions. I guess they are fairly frequently asked. I've asked the first one myself on GitHub 2 years ago, I think. And I think you answered. So kind of thing you'd expect to be able to do in a C program is call a function more than once. And in P4, you can call the same control more than once. But can you apply a table more than once per packet? In most P4 implementations, you can't. Why? What a weird restriction. Tables typically, if you're going to process packets at 6 billion per second, these tables are typically implemented in high-speed SRAMs running at multiple gigahertz or high-speed TCAMs running at multiple gigahertz. Once you've searched them once per packet, it's done. The next packet's coming in and needs to search it now. So if you want two packets that happen to have the same contents and do the same kind of actions in the same search key, just instantiate it, copy and paste it, do it twice in your program if you really need to do it, and have the control plane install identical or different entries in each one, your choice. Another common thing that you'd want to do in some fancier things is, can I, some layer 2 switches can do source MAC learning, a learning bridge, and they can do it in hardware at line rate. So they can do a lookup in a source MAC table. Is it in there? If not, automatically add it. Remember, it was on this port in hardware without talking to any external CPU. P4 doesn't have any defined semantics for doing that. Somebody could make an extension in their architecture if they wanted to provide a way to do that, install entry from the data plane itself. There are plenty of switches out there that do hardware-assisted learning. Instead of, when you get a source MAC miss, instead of installing an entry right there in the data plane at line rate, you send a notification message. You forward the packet however you would normally forward it, but you also send a notification message to the nearby control plane CPU saying, I received something with this source MAC and this input port with this VLAN, do what you want. And typically the control CPU would be, there'd be a processor responsible for deciding which new entries to add to the tables, the MAC tables. So yeah, the P4 program is just part of a system. It's not a complete system. Let's see, what happens if you reach a reject state? It's architecture dependent, but in V1 model, it actually doesn't do anything different than if you go to accept. But some architectures might always drop such packets. Some of them will save a little, in the standard metadata, there might be an error, a parser error status field that you can then look at in your ingress code and decide what do I want to do with parser error packets. And how much of the packet can I parse? That is chip or implementation dependent. A lot of them can do, I think, 256 bytes is, I doubt there would be any that would do less than 256 bytes. Whether they can do 1,000 bytes or not is probably more iffy. All right. Take a breath and ask questions there.
This is great stuff, but that last piece got me a little worried. So we've been looking at V4 and kind of simplish cases like that. If you've got V6 and you've got lots of extension headers and stuff tucked on, does that mean you might get to a point where your P4 program is kind of going, well, I thought I was going to get to the address, but I've run out of my parsing depth. What do I do? Is that also architecture dependent as to what happens if it doesn't find what it's looking for?
Ask your P4 programmable target vendor before you deal with 1,000 byte V6 extension headers, and they might tell you maybe you might want to rethink that as your.
So these are great chips, but not magic.
Well, so I mean, there's a lot of high-speed switch ASICs that, I mean, they all have finite limits on how many bytes they can go deep, which are probably not wildly different than the programmable ones. V6 extension headers, skipping them, if you need to skip over them and find the TCP or UDP header to do like layer 4 ACLs, talk to your vendor before you count on it working the way you expect it to. It's on the edge. It's on the bleeding edge, I'd say.
I guess the previous question sort of addressed what I was thinking about. Beyond the size issues, just the idea of parsing your way through a non-fixed header, right, is I'm looking for the transport ports in V6. And so our examples so far were very fixed header-ish, or maybe tunnel or not and fixed header.
So here's something that
without loops, how do you do that?
Here's something I would say that is very reasonable for probably most P4 implementations out there. You pick some number of, let's say you pick IP6 hop by hop extension header and destination options and routing. Pick 3 or 4 types. They all have a type and a length encoding in the first 2 bytes in a fixed place. From that length, you can, if all you care about is carrying through, finding the TCP or UDP header after them and then copying the option headers without looking inside or modifying them, that's a much easier job than looking inside and modifying them. Like if you want to IP6 segment routing, like, you know, that's kind of, again, kind of bleeding edge, check with your vendor. But if you just want to parse past and look for TCP and UDP, up to, you know, some number of bytes, a lot of devices will be able to just skip over them, find those, use those TCP source and dist port in an ACL, and carry through the IP6 extension headers unmodified. Or remove, maybe you want to remove some of them or something like that. But if you want to actually look inside of a routing header, the best ways that I know of are, okay, well, you decide when you're writing your program, I'm going to handle up to 4 V6 addresses in my routing header. I'm going to create I'm going to create like 4 different headers, one for one routing IP6 destination address, one for 2, one for 3, one for 4 or more, and actually have like different actions for handling those. So again, it may sound low level, and it kind of is, but it is possible on many devices to handle a small number of cases like these. But yeah, talk to your vendor if you want a P4 device that can do these things.
Is there any examples of that? Just the structure of it, I'm having a hard time envisioning.
I have a separate, my own public GitHub repository that I can talk to me afterwards, and I'll give you a link. I don't have a way to write on a board or anything, but I have some like example programs that show at least skeletons of how to approach these things.
How do the control planes populate the various tables? So for example, if you're doing some sort of routing protocol, is the table with the route table, is that get updated by whatever the vendor that implements the P4 implementation does, or is there some standardized provision for writing that kind of code and logic to get it into the tables?
So one thing that we probably won't get into, there's a couple of standard-ish or de facto standard protocols for the API that the control plane code would call to say, I want to add entry to the table named IPv4 table with this set of keys and this action and these set of parameters. How to just bundle those up into an API call in Python or C++ or Java, and then serialize that across a TCP connection and send it to a device and have it do that. But as far as, like, can you go to a Cisco NextOS or iOS XR control plane and have it work with an arbitrary P4 program device? If there's no, I can write a P4 program that doesn't have a longest prefix match table for V4 destination addresses. What is OSPF going to do with that? Nothing. It can't, there's nothing to program there if you write a P4 program that doesn't include that. So P4 is meant to be flexible, but it also means either you use a standard control plane and put a lot of restrictions on, I need at least this stuff in the P4 program, or else the control plane is invalid, it doesn't know what to talk to. Or you need to write your own control plane code for your own custom P4 programs.
Yeah, I was asking.
If that answer your question or not.
I was asking the other way around, like you want to experiment with your own routing protocols, your own like route learning protocols type of thing.
If you want to experiment with your own routing protocols, having a programmable data plane is an awesome thing.
Right.
It's a great thing.
But then it's all up to you to figure out how to do that then from based on this.
You own your destiny.
Okay. Fair enough.
You own whatever troubles you wish for, and some you don't.
Hi. I have 2 simple questions. One is, how do you support load balancing? I mean, I didn't see any random function.
Yep. A common, defined in V1 model, there's an extern called an action selector. And this is, things like equal cost multipath ECMP and lag, link aggregation group, typically using a hash function. You hash some fields of the header. So in a P program, you can actually, if you want to hash on just the source and desmac or just the v4 source and destination address or the L4 fields, you get to pick in your P4 program which fields of the packet you want to hash on. And then that hash value can be used to pick one of a list of n table entries installed by the control plane that go to one of n different routes or n different ports.
Okay.
So there are primitives in P4 meant to make that job. You don't have to write the hashing yourself. You can call a hash function. You can say load balance over a variable number of paths.
Okay. And one other follow-up question. So can you add, is there any restriction on the number of MPLS labels you can add in the header? Or do you support even?
So the one case where you can actually have loops in a P4 program is in the parser. I mentioned briefly earlier on there's a construct called a header stack, which is kind of tuned exactly for the MPLS label stack case. Effectively, it's an array. A header stack is an array. They call it a stack just because there's push and pop operations, similar to push and pop, but you can just treat it like an array if you want. So you have to pick a compile time typically for most targets. If you want the highest speed targets, you have to pick what's the maximum of MPLS labels I want to support in packets I receive and process, or I want to be able to parse. Any ASIC has a maximum number that it can parse to. 5 or 6 is where most of them, I think, peter out. You can write a P program that keeps going for 8 or 9 or stops at 3. You get to pick in your P4 code. But having so the parser can actually loop looking for the end of stack bit, let's say. But what a compiler for a high-speed target typically would do is, well, it'll look and say, oh, you define that array to be 3 elements. I'm going to unroll the loop for a maximum of 3 times. And so it ends up being a no-loop program in the middle of the compiler somewhere.
Okay, thank you.
Any other questions? Looks like we filled up our time.
I think so.
Hope we didn't bore you too much. Feel free to ask questions afterwards if you have any. I'm happy to stick around for a bit.